students in the BE program, and like Lester, we decided to do our own project, not take one off of the list, have something that we have total control on over the entire build process. So if we want to do something else because it's more interesting to us, we can do that. We have more control over it. Like Lester also said, this is a autonomous sensor platform. Basically what we want it to do is have an extremely adaptable design. If we wanted to mount some sort of sensor on here and drive it somewhere, let's say like a methane sensor, and drive it autonomously into a mine and then have it come back, we'll be able to see what kind of data comes back from that sensor rather than having to send a person in there. Like I said, the whole point was to have an adaptable project that we can kind of market if we wanted to all different areas between military, defense, the gas and mining industry, stuff like that. If you'd like to talk about the sensor.
Oh, we used Sony, Sharp sensors. We used the short distance, which are about 30 centimeters for the corners, and they would track, say, if we would be going adjacent to the wall, they would back up and turn and follow along the wall. The long sensors are for anything in front, to the right and left and rear. And we also have a backup system, which is the sonar, which are the round objects on top of these boxes. For the, in case if, say, ambient light got different for the IR sensors, or noise in a factory would alter the sonar. So we chose multiple systems for detection on this, so it would not hit anything or damage our vehicle.
Basically cover the weak spots of each different sensor. If you see on the back here, we do have an antenna. It mates with the antenna over there, the base station. We do have a RF uplink, so we can wirelessly track and monitor system data. On this left side here, there's a GPS chipset, so we actually relay GPS coordinates over to that and into whichever PC using a USB to serial port. So any person that wants to monitor our system simply plugs it into any sort of laptop, runs an application, and there's an embedded copy of Google Earth that we actually programmed specifically for this project that will take the GPS coordinates and then plot it and then snap to that exact point on the map. And like I say, it's embedded, so it's cached locally. You don't need an internet connection. So if you only have a standalone system out in the field, then you're still good to go. Also on the back here is the power input. We wanted to internalize the battery charging process. That means you don't have to break the top off, get out the bolts and stuff, get your little alligator clips, and actually touch the batteries to charge it. You simply plug cord in the back, set which battery you want to charge, flip the switch down to charge, and when it's done, the LED tells you to switch to the other batteries. While we're talking about batteries, we have two battery packs in here. They're made up of 1.2 volt, 10 amp hour individual cells. One drives the electronics, the other drives the motors that we have. We have 4 motors driving, one for each wheel, using a roller chain configuration. Like I said earlier, we had total control over the design process. This is one of the things we wanted to make sure that we had, because with 40 battery cells,
40 batteries.
This thing weighs 40 pounds, 50 pounds, and we wanted to make sure that we weren't stressing out the axles with all that weight. So we opted for the roller chain idea, so that the axles get the weight and not the motor shafts themselves. The sensor arrays up here on the top, you gentlemen probably can't all see inside here, but we do have a microcontroller that is running the show. It gets all the sensor data, and that's where our navigation algorithm is kept. It interprets the sensor data and does the transmission and imports the data from the GPS and stuff like that. It is a Digilink part, chip kit Max 32. It's lots of I/O, 86 I/O ports, 4 serial ports. It was a perfect match for us since we have so many serial interfaces we need to interface with.
We have a RoboClaw 2 by 30 amp motor driver, which controls each side, which is skid steer, and the motor driver sends serial packets to that to tell how far to back up and which way to turn, and we all can confer that with the RF uplink that we have, and we can send information and receive information on where it is at. The bi-core voltage regulators They supply the power to chip kit, the lights, the fan, all the working components, all the subsystems in this chassis that we have here.
We actually started out, we wanted to make our own regulator system using the analog courses that we've taken through here, the knowledge that we had from that. And we kept having problems with overheating using the parts we had available to us, so we ended up deciding to go with Vicor Power's individual regulator solutions. And they were willing to work with us and give us an educational discount kind of thing, since this was for a project. And the 3.3 volt, we have to run all of our sensor hardware off of 3.3 because that is the limit to the chip kit's A to D converters. So we had to make sure that we had very, very close, because if we change that voltage going to the sensors at all, they're ratiometric. So if we change the voltage going in, it's going to change the voltage that's coming out. So if we raise our voltage by 1/10 of a volt, our distance is going to be off by however much that correlates to each individual sensor. So if our voltage is off, we end up smacking into a wall, and that's well, it's more dangerous for the wall. Let's be real. But
The other thing is, though, we found out was when they built this, we had this built, but we put all the working components in here by ourselves. They also installed lights on here, so we can actually control it with this switch so that if it's in here, the lights don't turn on. But if we go outside when it's dark, the lights do turn on. So it does save on the battery, and we can also tell where it's at sometimes.
yeah, like you said,
See where it's going.
yeah, I'd have to take the front panel out, but we actually built our own dusted on sensor with a potentiometer, so we can adjust, when the light flicks on, when it flicks off. And we included a hysteresis circuit, so it's not strobing, and when the threshold's just barely above or below, saves a lot of battery time, because they're like 2.5 amps per headlight, so they pull a lot of juice, and they put a lot of light out. On this side also, we have a digital compass that also feeds heading information into our microcontroller. We use that to determine how far we've actually turned from our original course. So if we come up to an object and we want to turn 90 degrees, we take an initial heading, and then we wait till that differential is 90, and then we do whichever turn or whichever direction we want to drive on, which it's a lot better than trying to sit down and calculate, how long do I want my turn to be, rather than just doing something simple like how many degrees do I want it to be. What other analog circuit do we have to build for this?
The shunt circuit. The
That's
shunt
right.
circuit was our main problem in the beginning. We did go through one motor driver, was because of a high voltage spike, which went above the maximum of 30 volts. So we put this shunt circuit in to not let it go above the 10 amp output of 30 volts, so it will save the motor drivers.
It is a crowbar shunt using an SCR, so whenever the voltage pretty much makes a diode conduct, it shuts that gate of the SCR and then blows the fuse and hopefully saves the motor driver. While I say hopefully, this morning, actually around 6 o'clock, we had this thing up and running. It was doing its autonomous goodness and has ceased to function since. So that makes another motor driver that we will be returning to the company that sold it to us. That's one of the things we'd like to do different if we were to make a second revision to our design, is actually up the specifications on our motor driver. So we don't have to rely on things like shunt circuits, something we have to build secondarily to try and make sure we don't exceed any sort of limits. Is there any questions we can field for you gentlemen?
So you have like a mission development software, so you give it a map that you want it to follow, or how do you send it on its way?
The way it works right now, you just kind of point it in the direction and it goes till it needs to make a decision on where to turn. I actually have an independent study course next semester, and I do plan on developing this algorithm more, as well as finding other cool things I can do with the RF uplink, maybe sending it GPS coordinates, things like that, to try and make it a little bit more of a smart application. Anyone else?
When did you graduate?
Next fall, the same as Mr. Roble.
Maybe consider any video?
Yes, as you can see on the top plate, we left lots of room on there. That's one of the other things we wanted to do, but finding a rugged construction and waterproof camera, as well as a wireless uplink system to relay it, was a little bit outside of our budget range. So we're kind of hang off on that idea, for now at least.
What battery technology?
They are nickel metal batteries. So
Why
that's,
did it 767
By
curves?
boat, yeah. Oh, yeah.
we had considered doing the LiPo option, but again, the budget really squashed that idea down a little bit.
So for right now, it doesn't run?
No, it does not. We can show you the
There's one-
GPS uplink, stuff like that, but
How's the GPS work if it's in a mine?
well, that's another budget consideration. We're just using a no gain antenna right now for a GPS signal. One of the things we'd like to, on the second revision, if we do one, is to have a high gain antenna, or find some other way that we can find out where we're at if like you say, we're inside of a mine and we can't get that GPS signal.
Can your ultrasonics range find? So you could build a map real time?
Yes, that was actually, in the beginning, we had considered that as an option, and then we realized the complexity that was involved in it, so we kind of put it aside a little bit, if you know what I mean. But, yeah, that was a possibility in the beginning.
That's cool.
Anyone else? All right, thank you very much for your time and attention.